Good morning, and let's get started with the second part of the runtime environments story. In the first part, we saw how hardware and software need to come together, and through concrete examples about how we actually work, we saw how they actually do come together. What are the things that uh, each stage does to match with the rest? That was, in some sense, a little deeper view about what we actually do. The motivating idea there was we need to construct, we need to have a software construction process that will create the final binary according to what is needed by the underlying machine. And we also saw that the notion of underlying machine can be now be generalized also. Okay, it could be different hardware, it could be different operating system that is, or another system software that is existing on that other system, and so on and so forth. All right. For example, the Android system has a slight, although it uses the GNU Linux kernel, the other system software is different, and therefore the kind of things that we need to do to construct the binary are slightly different. So in this part of the story, we will now take a more deep view, and we will explicitly look at what needs to be done by individual tools. However, we will come to a point where we will state the motivation and the purpose very well, but the algorithms will be not necessarily discussed because, to be honest, they are the kind of algorithms that are there are typically some things that you study elsewhere. Anyway, so apart from indicating that, okay, these are the kinds of algorithms that we could use over here, there is not much from that point of view. This is more of the engineering mindset that really gets developed over here. Okay. The implementation aspect about how actually algorithms come together to realize concrete things. The design and implementation side of the story is what is the one that we will see in this second part of the runtime environments part story. All right. So if I were to really summarize the plan for session two, this is how it is. We are really going to look at dynamic memory and function activation as the two main parts. Uh, there is some amount of algorithmic component over here, but again, it's going to be indicative. But one should really look at also the data structures point of view that these runtime systems, support systems come up. Before I continue, I have I'm curious about certain point though, and I'd like to know how many of you really knew about runtime systems before you came to the school. So, or let me invert the question. How many of you, how this topic of runtime systems is new to how many of you? Can you just write it in the chat? Just quickly write it in the chat if this topic of runtime systems is new to you. Let me just look at the chat window. Okay, some concepts are new to me, says one of you. All right. The reason I asked is during this break, I remembered a story some incident that had happened to me a long time ago, somewhere, long time ago, 14 years ago, 2007. So I was speaking at a conference on free and open source software in Bangalore, and I was speaking on the GCC internals. I was supposed to speak on that. And before me, there was a talk by, uh, I'm not sure if you know this guy, Ulrich Draper. Okay. Ulrich Draper has been a contributor to open source since quite a long time, has been maintaining the GNU-C library, and has been programming at systems level for quite a long time. He was with, if I remember it right, he was with Red Hat in those days. I don't know what is now. We can just search him up and we can find him. So the topic of Ulrich's topic was the basic runtime. Okay. So he wanted to talk of the basic runtime, and as it stands, the introduction, the person who introduced Ulrich, that person mentioned that he was going to talk about the basic programming language. Whereas the real intent was, of course, talking about the runtime systems in the way that we are talking. And quite expectedly, Ulrich was quite mad at him. And when he began his talk, he did mention that at least people should know what the hell is the meaning of runtime in a talk in a conference like this. This is not a end user conference and so on and so forth. Which means that he was quite disturbed by the idea that people do not know what is runtime. I remember that incident, which is why I just asked this, that how many of you guys really know what is a runtime system? That was the thing. So anyway, thanks. At least some of you find that there is something new. Great. So let's continue. I mean, I should have probably set up a quick poll. That would have been useful, but it did not strike me. It was a late memory. So in this session, we are going to look at some real runtime problems that are there, that we need support for dynamic memory, function activation, and all that stuff at runtime. And we will, towards the end of this session, come with the key idea in this entire business, the idea of binding. It's possible that this idea might have been introduced to you earlier, and very much possible that it has been introduced earlier in this particular school also. So do excuse me if I sound a little repetitive, but I believe that there is something new over here also. So let's begin the story of runtime support, the second session, by trying to understand what is it that is dynamic memory from an end user point of view, and go back and try to see how we can realize it. Similarly for function activation. All right. So let's start from a point that we sort of know. So I'm going to look at the idea of a high-level language, and C is going to be my example language. All right. So you could have your own favorite language, could be maybe Java, C++, or God knows whatever it is. The ideas that are there in that high level language, we are just putting them up over here. So those ideas can also be added to this one. But my point is not to be exhaustive about the ideas, the programming model that your high level language offers you, but to be indicative. So let's see how that goes. So variables, for instance, are an abstraction of memory locations. Functions in C, a sort of abstract computation. That is, they are kind of black boxes that transform parameters passed to the value returned. And in particular, you write the function once and use it many times. But that actually is the essence of computation anyway. You describe the process and apply to many different specific instances. In C, the function calls are in LIFO, last in, first out order. So we say that the caller is suspended until the callee returns. Okay, and the C system views a program as a set of functions that start from a function called main. And then there are many others also. But what I'm really looking at is when I start talking about variables, functions, function calls, etc., like this effectively is a kind of a thinking model that C as a language allows us to think our programs with. We are going to think our programs in terms of variables, functions, function calls, and so on and so forth. That's the idea. All right, that is what C gives. Maybe if it's a language like C++ or Java, which have classes, then the model is different. I mean, you use classes as your way of thinking about programs. Okay. What we already know, something that we have also seen in the last session, is our typical sequence is from a source code, we construct our assembly code, from which we construct our object code, from which we construct our executable code, from which we construct our process. Okay. The source is very high level. The data types are at that hour, meaning high level. There is a logical control flow, and so on and so forth, something that we just saw. And we do think of target hardware as very low level, particularly in terms of the rigidity. So there is strict addressing, only finite integers are available as data type. So the values of data type have a limitation. There is a lower limit and the upper limit to the possible values that can be stored in the data type, and so on and so forth. That is what occurs because of the rigidity. All right. Now, let's see how this process of transformations that we had seen in the last session, compiler, assembler, linker, loader, and so on and so forth, what are thinking models it gives. Okay. Note that ordinarily we think of these thinking models only in terms of the high level language, but I'm going to do this for the intermediate stages also. Okay. There's a reason I'm going to do that for. So let's see that. This is an exercise that is probably understood by each one of us implicitly, and I am only making it very, very explicit. So when we think of the C language as so a thinking model for source program in terms of high level language like C, it's a very logical model, very near to the human level. Well, as far as C is concerned, it's debatable, but nevertheless. So whatever are the operations and the logical data types that are there, they are very much at human level. And the entities in the program are labeled using symbols. And there is no concept of an address at all in a high level language. Okay. And if at all it exists in a language like C, it is behind the scenes. I mean, we do explicitly talk of addresses, but they are behind pointers. It's in that sense they are behind the scenes. As far as assembly programs are concerned, the operations which were very, in some sense, logical, that is very much near the human level, are now explicit in terms of the mnemonics, and the data types are machine data types. Okay. In assembly programs, locations, that is addresses in the programs, can be logically labeled using symbols, okay, or labels. But the concept of an address is, as it denotes locations, is very, very explicit. It's a finite set of positive integers in an ASM program. Because, I mean, you could use addresses or labels. You have a choice. In an object file, your operations are not mnemonics, they are explicit binary codes called operation codes, opcodes. There are explicit machine data types. The addresses are in binary. Okay. And in particular, in object files, symbols whose addresses cannot be computed are just tabulated as undefined. Okay. So you have two kinds of tables, the set of symbols with addresses and symbols without addresses. That is what is there in an object file. An exe file is pretty similar. Okay. Uh, Usually most of the address symbols have addresses, but there could be some symbols whose addresses are not computed. And we expect that to be done by the loader or other pieces in the system software. As far as processes are concerned, now you get very, very real. There is no the operations and machine data types, etc., that were there now actually need real resources like memory and CPU time and so on and so forth. So you have management algorithms to allocate the resources. All right, you have memory management for allocating memory, you have CPU time management for allocating CPU time, that is scheduling the CPU. Okay, many processes can be generated from one program now. Okay, but it's at this point that addresses in program code need to be updated when memory is allocated. In particular, this is what relocation is about. What we are really thinking here is this, that in general, my program binary could be loaded at any area in the primary memory. I also know that my machine code is very strict. It requires the exact memory address from where operations are to be done. So if I make any error in the address, then the behavior can be anything. It's just undefined. It can be anything. This means that once I write a binary, if my addresses are fixed, then where that binary must exist in the primary memory is fixed. If I have such very rigid memory addresses, then I cannot take this binary and load it elsewhere. So that I can relocate this, I need an ability to generate the addresses in the program code, get them updated when the memory is actually allocated. Okay. This is what relocation is about. One simple technique is, of course, using the relocation register. The relocation register contains the offset to be added to every address in the program, and this is done actually by the hardware. So you don't really need to fix the addresses in the program code at all. You just, whatever is there, you just load the program anywhere and the relocation register will take care of it. All right. These are what the thinking models allowed us to do. As you can see, the thinking models change. They are very near to the human way of thinking as far as the high-level language is concerned, and they gradually approach the machine level as we progress through the tool chain. This is the key observation that I need you to take through this discussion, that the thinking models gradually move towards the target machine, gradually being the key operative word. All right. Here are some details now. A compiler is going to translate from source to assembly. You will hear more about compilers in the later part of the school, but the data types, control flow, and operations, etc., are some things that your compiler deals with at source and assembly levels. Okay, so data types called integers, characters, and strings have to be converted to one or more integer strings in assembly. Control flows like loops and function calls need to be converted to target machine sequences and branches as addresses as labels. And the operators of the source are to be converted to machine instructions. This is the transformation, roughly speaking, that a compiler needs to do. In contrast, an assembler is going to perform translation between two thinking levels, the assembly level and the object level. So integer strings need to be converted to one or more bytes. The control flow, machine sequencing and branch needs to be converted to machine instruction opcodes and numeric addresses. And of course, machine instruction mnemonics in assembly need to be converted to instruction codes. Now let's look at the pragmatics of assembler and linker, something that we had a glimpse before. Let's look at them in a little more detail. Bear with me, you will have to go through the details because this is a systems level work and the devil is in the details. So what you see beside you is a disassembled listing of binary. Okay, so you can see the assembly code on towards the rightmost side of the story of the slide, and somewhere in between you can see the numbers. But we will see that in detail. So the assembler starts defining regions called as the text region, which is supposed to contain instructions, the data region that's supposed to contain the data, the BSS is supposed to contain uninitialized data. These names, by the way, text, data, BSS are traditional from the Unix world, and most of these terminology is common across these tools across various operating systems. But there can be some differences. One must be aware of that. So there are various section names. These are called as section names, the text, data, and BSS. So what is occurring over here is that the assembler is trying to take your source program, the C program. This is how the C Pro compiler should work, that your source program should be converted to regions, sections of instructions, sections of data, and sections of uninitialized data, and so on and so forth. There could be other directives also, which global tells you what the global variables, type describes the types of variables, and so on and so forth. Okay, but the point I'm bringing out over here is that your actual assembly language program is defines a program in terms of sections of instructions, data, and various other sections. That's point one. The unit of addressing is a byte, of course, and it is always assumed to start as 0. Why is that? This is because this assembler is expected to work on a virtual memory system, the system that supports virtual memory. Therefore, every binary is supposed to be loaded starting from address 0. Any changes in the addressing will be taken care of, should be taken care of, and can be taken care of by the other parts of the system software. In particular, your operating system is going to perform the memory management and translate these addresses to actual physical memory addresses. All right. That is why the starting address is assumed to be 0. What I'm bringing out over here is that you are going to build your tool, the assembler, such that it is cognizant of the target system, the way the target system is supposed to operate. This was one of the things that we learned in the last session. Okay. What I'm doing over here is showing you explicitly what are the stuff that is happening, some of the things that we learned there. That is why it's a repetition, but I believe it's worth it. You need to look at the details. .ro data is supposed to be a read-only data section. Okay, so the data in binary is the set of numbers that you see in your third column around over here. Okay, what is the data that it represents? You can see slightly towards the right that it's a dot string, a string kind of a data. A equals %d, comma, b equals %d, blah, blah, blah. That entire string is a set of bytes, and those are the bytes that are exactly being pointed to. This is again affirming my story, confirming my statement that whatever are the data types in assembly, we need to convert them to bytes. This is the original data in C, which has been just taken up as is in the assembler. This again reiterates the earlier part. Why did we assume the address to be 0? Okay. The only thing is that note that there is a change in the section. Now it is a text section. Earlier here it was the BSS section. Okay. Different segments. Sections correspond to segments, will correspond to segments. And this only means that we are really treating instructions and data as different segments. Why are we doing that? Because that is what the hardware needs. If the hardware does not need it like that, for example, one of the questions was, what if we don't have segmentation? Well, then you construct your tools accordingly. This is what it means. Here are some labels that are used by the assembly program for the text section. Okay. Perhaps you know that labels in an assembler are actually translated to memory addresses. Notice that main is the name of the function in C, and that has been translated into a label in assembly. This is the reason why names of functions are pointers, because these labels are just addresses. Okay. What you also see is that a single, there can be more than one label per address. There are two, the labels main and .lfb0 are two labels for the same address. Okay, that will map to the same address. You also see instruction mnemonics now, and their register numbers as operands. Okay. This is the instruction opcode version of the instruction mnemonic. All right. And the opcode encodes the various register numbers as an operand. So you only see the opcode as one single number. So if you, for instance, expect push Q %RBP, %RBP is the argument. And if you think that that should also be a separate number, that need not be. The entire push RQ %RBP is just one number, 55. I say it as 55 because this is hexadecimal. And if 55 would imply that it's decimal. This is definitely not a decimal number, it's a hexadecimal number. So the correct pronunciation is 55. You do not say it as 55. All right. Continuing the look at the assembly code. Here is one part that you see. Here is a call to two functions. One is a modify function, the other is a printf function. They are seen as labels. And the question, of course, is where is a label in this file? Perhaps the modify label is, there you see the modify label in the file. Somewhere that modify label did exist. Great. All right. Fine. It's in some other file, modify.co. That is why you see it as address 0, even if it's a text section. The natural question would be, how can the text section have an address 0? I already saw that. But well, that was in a different file. All right. So this is the kind of a scenario that we are talking about. We have a C program with two different files, and you have one fellow that is in one file being called by the code in another file. You see that reflected in the assembly versions. Okay. That is why when the assembler will assemble this, it should keep a list of two tables. One is a table of all the labels that it sees that have an address or whose address can be computed. And another is a set of labels whose address cannot be computed. There is insufficient information to compute that. Okay. It's at this point that the linker enters. The linker takes a set of object files and looks at the two tables. The undefined labels from one object file must be defined in one of the other object files. Once you find a definition, the linker is able to resolve the undefined addresses as defined ones, because once you know that they are defined, you know where in memory they are. Let's see the linker side of the story. This is the output of a linker when it is linking a bunch of object files, including the C library. All right. You can see that the C library was needed for our program sample.o, because sample.o had a printf call to printf, and that printf was in the libc library. Okay. By the way, you also see the C runtime part. We will come to that a little later. Here are the set of symbols that already had some addresses in that particular file sample.o. Okay. If you look at the output of this linker, you will find that there are sections .text, 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 and so on and so forth, .data, .fini, and so on and so forth. And in the .text section, you will see that the linker has arranged the binary version of various functions. Not only you see the binary that it has arranged the binary versions, you see at what address it has set them. You will now see your C program in terms of the binary, the way it has been laid out in the virtual memory starting at 0. Okay. The linker is going to simply assume that the binary is going to be loaded in virtual memory, and therefore it starts the address computation from 0. That's all it does. Okay. You will see that the .text contains starts with some scrt1.o, then crti.o. The scrt1.o contains a function called as underscore start underscore start. Then you have crt begin s.o. Then you have your actual code that you have written in your C program, sample.c program. It contains a function called main. The modify.c contains a function called modify, and so on and so forth. All right. Towards the end of the section, you will see that there is a crt ends.o, crt end.o. These were not the things that you had written in your C program. These were included by the linker, and they were supplied by your compiler. That is, the GCC compiler pre-built created these things already for you, and using the linker, these were attached before and after your C program. Okay. Here we very explicitly see what is the runtime that is being added by the linker to your C program. All right. Notice that the linker has loaded these files. srt1.o, crti.o, crt begin s.o, sample.o, modify.o, and libc.so. And maybe some others are also there. I'm just indicative over here. So your sample.o and modify.o are your C files, your C programming files, and they have been packed between some other object files before and after them. Okay. This is what we had seen. We had seen very explicitly that from this file, from the file scrt1.o, the function called underscore start was used, and so on and so forth. We see how the linker is helping us to create the illusion that main is a function. Why are these things being inserted? Why is it that we have crt 1.o, crt i.o, crt begin s.o? Why are these being done? Let's see that in a while. But before that, let's revisit the exe to process conversion again. We had seen most of this, but as usual, there is a little more that I'm going to add over here and build up our insight. Okay. So notice that exe, the executable, is just a file on your secondary memory. Okay, somewhere in your directory tree, there is this file, the executable file, right? And it contains your code section, the .text, data section, .t, but all in binary. Now, what is an operating system going to do to this exe file using its loader part? All right, what is it going to do? The task of an operating system is to construct a process out of this executable file and run it. In order to construct the process, it's going to use the contents of the executable file. Looking at the contents, it's going to allocate primary memory, load the contents of the exe file in the primary memory, set up the initial values of data, specify the first instruction to execute, that is the entry point, and add the scheduler queue. This is what we had seen before. Okay. And again, this is what we will see through a little bit of an animation, something that we had done a little before, but let me repeat that. There is something that I want to add. Let's go ahead. You explicitly see the OS in front of you in the memory and the scheduler queue SQ. There is some scheduler queue that is there. Of course, this is not a session on operating system, so we are going to think of just one scheduler queue. Real operating systems use multiple levels of scheduling, but that's a separate part. Okay. You also see the executable file in terms of a set of bytes, the executable data, executable code, and maybe other parts also. Okay. So first of all, it loads the executable file for reading. I mean, see, how do you read a file? You have to load it in primary memory somewhere and then write code which will study it. Where does the code part begin? Where does the data part begin? How long is the code part? How long is the data part, etc., etc. All of this has to be found out, and which means that the executable file has to be loaded in the primary memory anyway. Okay, once you load that, you read that. The OS will read the executable file and get the information. The information that the operating system gets is the size of the code segment, size of the data segment, and so on and so forth. Using this information, the operating system is going to allocate primary memory as needed. Okay. Over here, I have shown that the executable file that was loaded was in some sense disappeared, but please do not worry about that. Note that using that information, the operating system has allocated memory for loading the code and data. Okay, you initialize the memory regions as needed. So you might actually also create a stack. This is also what we had seen earlier. Okay, the executable code is copied, the data has been copied, the first instruction from the code section is now entered into the process control block. That is the entry point. All right. This all has been collected into a data structure. And this is the data structure that is given to the scheduler queue. The scheduler queue actually is going to scan through this and schedule each one of them according to the position in the queue. All right. And whenever the process gets scheduled, at that point, what's going to happen? The entry point is going to be loaded in the instruction pointer. And your CPU will be made to jump to the first instruction in the executable code. Why? Because it points to the first instruction in the code part. That is how it will begin. Of course, you also set up the data segment pointer. You also set up the stack pointer before you start executing the code. All right. So all these setups are made and the corresponding CS, IP, DS, DX or other registers, SS and SP registers are set up and then the jump is made. Okay. That is how the scheduler code is going to execute the process code. All right. This is a slightly new piece of information that is there. I just want to show the hardware and software coming together, the first view. Now the program is ready to run and will get executed when it is scheduled. Okay. So when the CPU executes program, when the scheduler schedules it, it's at that point the machine begins changing its states according to the program. This is what a process is. All right. This is what a process is. It is critical to understand this idea of a process because the entire idea of computation is to really actually execute processes. Okay. The process execution as a focus is something that is required. That is what end users of computers do. And people who are in this profession, for them, it's not only executing processes, but building them. That is also their side of the story. They are the ones who build the processes. How do they build processes? By writing programs and make use of the other system software that will generate processes out of these programs. Okay. Let's now come to the next part of the story. This probably whatever we have done is may have been slightly familiar, but I hope there is something new. But let's go ahead with this. What I have in front of you is a kind of a sample C program. It just does factorial. Okay. And there is a piece of code that is commented out, but mainly because I'm going to look at two different parts of the thing. It does not matter whether this code is going to make sense or not from a usability point of view, but as far as illustration is concerned, this will work. We have already seen how the factorial, this factorial program, how will it work? What I'm showing over here is the view of the primary memory, primary virtual memory, from the point of view of actual execution of the code. Notice that the stack is growing downwards from the top of the image to the bottom side. And otherwise, we are assuming that memory is growing along the upward direction from bottom to the top. I've also shown segments, the core of the core segment of the factorial process, the data area, data segment of the factorial process, and the heap section of the factorial process. To illustrate the heap, that is why I had those pieces of code in the comment, in particularly the malloc side. So when we consider the operation of a heap, we'll come to this. So I'm assuming that for concreteness, we are computing factorial 6. So when your linker has set up the main activation for main, we see that activation towards the upper side of towards the lower side of the stack that looks in the upper side of the memory. That is the activation for main. What is an activation? We'll see that. We'll see that. The key question that we have is, how are these runtime structures realized? Heap memory, data area, code area. That code area, data area seems all right. But what about heap and stack? What is the role that these fellows play? Why is it that I have this idea of an activation record and I'm saying activation of main is activated? What is activation? Why is it that I'm using stack for this? Let's see that side of the story. The activation is required to support the idea of a function call in a language like C. So in my C program, I had a main function that called another function called factorial. All right. Main itself is a function as far as our C language goes, so it must be called by someone. All right. Who that someone is, the best approximation is the operating system itself. You can imagine that the operating system calls the function main. That's the best approximation to work with. So what does a function call have? The function call would typically mean that there are some parameters that are passed, all right? And the function is going to perform some computation and going to return the result. All right, so the function that is going to call will be called as the caller, and the function that will be called is the callee. What is it that I need in order to perform activation? I need the actual parameters to be passed from the caller to the callee. Now, how do you pass information from one place to another? Even if you have to forget computing, even if you have to exchange information with each other, you have to do things like agree on the medium, agree on the language of interaction, agree on some other aspects, like suppose you want to give a book to your friend, then both of you must decide on a common place where you meet and exchange the book. Or if your times are different, then you say that, okay, I'm going to keep a book at so and so place at some time, and you can then reach that place and pick up that book at some later time. But the point is, you need to establish some common area where exchange can occur. All right. The stack is the one that is used to do this because, point one, it is always, the stack is known to both the caller and callee. Okay. And second, the LIFO approach of functions that C has is a natural fit to stacks. So in C, when a function is called, the caller is suspended and the callee runs, and the caller resumes only after the callee returns. This is last in first out behavior can exactly be created or realized using a stack. All right, so that is why you have activation, that is the information that is required to be passed between the caller and callee, and these activations are arranged in a stack. That is why you see main factorial 6, factorial 5, 4, 3, 2, factorial 1. You see them going up the stack. Okay. What does each activation contain? Activations are also called frames. It contains information like the actual parameters, fine, the values of the parameters to be passed for that particular call. Note that the stack, this particular stack is a runtime object. This stack is constructed as your program runs. This is particularly for calculating the factorial of 6 in the example that we had. If it's factorial 7, you will have one more element in the stack. All right. So what does the activation contain? It contains the information that is shown like this on your screen. Actual parameters, return value, control link, access link, save machine status, local data, temporaries. These are the various kinds of information that are there. Let's quickly have some examples about what these information piece of information are. The actual parameters, of course, are the values to be passed by this activation by the caller. Return values will be the ones that will be returned by the callees. Control link is a pointer to the activation record of the caller itself. So that connects the callee activation record to the caller activation record. Access link would be pointer to data from other activations is needed. So think of, for example, exceptions. All right. Other pieces of information would be return address to the caller code. Okay. Restoring the state of the registers used by the caller. Okay. So if the caller has some registers and the callee uses them, then the callee must be restoring them when the callee finishes. So what the callee is supposed to do is, before it starts its work, it is going to store all the registers that it uses in this area. Whatever caller registers it uses, it stores its value in this area, uses the caller registers, and before leaving, restores them back. Okay. There is also space in the stack for local variables, the so-called automatic variables in C. Okay. There is also space that you need for temporaries, like expression values, temporary expression values. All of these are the kinds of information that is contained in a frame. This is one activation record. Okay. And as the program runs, it is going to have a stack of activation records. I hope you can see that this is a runtime structure and in no way can be realized at compile time. Okay. The actual contents can never be known at compile time, but the structure can be. So during compilation or while we create these processing systems, we can create the structure, but its structure will be used when it runs. This is how you would want to support the runtime operation of languages. Okay, so here is a little more detail. Who does this and how? The language subsystem, compiler or interpreter, creates this stack of activations. Okay, so here is the reality. The activation record construction task is typically divided between the caller assembly code and the callee assembly code. Recall that you have the C program is looked up as a set of functions, and it's possible that the caller can be in one file and callee can be another file. All right. So Part of the activation record construction is handled by the caller assembly code, and a part is handled by the callee assembly code. What part by caller and what part by callee? Are there any very general rules? No, not really. So, uh, at least I don't know. There is no exact division of labor between the caller and the callee. And it's only over time that some rules of thumb have emerged. So usually it's very implementation dependent, and that is why you always use a tool chain that is built with each other. Okay. So if your compiler is going to make some assumptions about which part is going to be done by caller and which part by the callee, then the assembler should also be consistently using those assumptions. That is what we mean by saying that the tool chain is consistent with each other. Okay. So there are some rules that have emerged, and there is an example that I'm showing over here, just talking about it. You can go through it. But the point is, as such, there is really no exact division. So you will have to really look at the details for your specific tool chain. The requirement, however, is that the tool chain must be consistent. This consistency must be there so that the runtime stack behavior is consistently maintained. What we see now is we are constructing our tools according to what we need the target machine, according to what the target machine needs us to do. Here is a very detailed example of that. All right. And you can also see that this is the construction of an activation record is primarily a data structures exercise more than algorithms. Let's go to the next part. But before we go to the next part, any questions? I'm going to talk about heap memory now, but before that, any questions? All right. So if there are no questions, let's go ahead. Let's now look at the same code, but with assuming that the memory allocation is being done instead of that f is a to I. Instead of that, think of f is malloc 20 into whatever and some stuff in that part. So whatever is a commented code is known as now uncommented. Think of it like that. Okay. The point is, if it's a stack, then the stack will disappear when the callee returns. Then the activation record that was constructed on the top of the stack for that callee will be destroyed. In other words, you are going to pop off the activation the moment callee returns. That is why the temporary variables are on that activation record, so that they just disappear when the callee returns. All right. In other words, when the local variable of a function goes out of scope, it disappears, or it is made to disappear. The programming language will say that it disappears, but we should now understand that it is made to disappear. Unlike the stack, a memory allocation will be actually existing, will be, once it's performed, it will outlive the function call. It will not automatically go away once the function returns. It has to be explicitly deallocated, that is freed up. All right. So a memory allocation is an area of memory that will remain with the program until it's deallocated. Okay. And this has nothing to do with the function calls, etc. Functions may be called, or they can be called, they can just go and disappear, and so on and so forth. All of that can occur. This is the other kind of a dynamic behavior that we need to support. The stack allowed us to support a behavior that is consistent with the scope rules. Now we want to think of supporting other kind of dynamic behavior. All right. We want such a behavior at runtime, and so we are preparing for that earlier. Okay. Now we focus on the heap part of the story. Think of the heap as a memory manager, essentially. All right. And what does it need to do? It must support allocation, deallocation. All of these can be of any size. In principle, any size. Of course, in practice, it will be limited by the amount of memory the system has, amount of virtual memory the system can support. But in general, for all practical purposes, we say that the memory allocator supports memory allocation of any size. What is more, the order of allocation and deallocation can be anything. All right. It need not be that the deallocation order should be exactly inverse of the allocation order or something like that. No such rule is required. While these are the basic desirables, we also seek efficiency. Despite all of these somewhat possibly conflicting and hard requirements to be taken care of, we want efficiency. We want minimum heap size. All right. We want operations to be fast enough. All right. Therefore, we want to use whatever hardware support we have, like the memory hierarchy that is there, we would want to use it. Typically, programs exhibit what is called as spatiotemporal locality of reference. We would want to use it. And we would also want to reduce fragmentation that can occur over time. What is fragmentation? Continuous allocation and deallocation on the heap memory produces holes, and that is what is fragmentation. It would be good to, one way to overcome fragmentation is to perform something called as compaction. This is what you typically learn in your operating systems course. So, all of these things, reducing fragmentation, exploiting hardware memory hierarchy, and stuff like that, all of these algorithms are pretty well known, but these are the things that we seek as efficiency issues in a heap memory management. As you can see, the basic idea of memory management is the same. So your algorithms for memory management, allocation, deallocation, whatever size and order, these are your typical algorithms that you have already studied in your operating systems course and can generalize them as needed. They are exactly the ones that are typically implemented, but with the kind of efficiency issues that we need when the memory management is occurring within a process. Okay. You can have a look at Douglas Lee's memory manager, the link that I've shared, where all these ideas are discussed. But again, because the algorithms are fairly well known through your OS courses, typically, there is no detail there. That's all. So, what is it that we have really learned in this side? We have really looked at details of some of the things that we had seen in the previous session. Now let's take a breather and look back. Before I proceed, I want to say that by compilation, now I'm going to be a little loose. Compilation typically meant that whatever is done by the CC1 program, but now I'm going to look at compilation in a broad, somewhat loose sense, that translation from source program to the executable, the entire thing. So it sort of includes the compiler, assembler, linker, and every one of them. All right. Let's look at the entire tool chain a little more relaxed. What is compilation really doing? It is gradually detailing out. So The variables idea that is there at high level is gradually being detailed to very specific memory locations that your hardware needs. The functions idea that you have at your higher level is being gradually detailed out to machine code instruction sequences that your hardware needs. Okay, and how is this gradual detailing done? Yes, we know that there is a tool chain, and we have seen how this detailed stuff looks like for an assembler, for a linker. That's what we have looked at. But if we try to understand what is really the idea that is common in constructing runtime systems over here, it is to associate names to hardware details. Okay, so what we really want is an association between the variable names of your high-level language to memory locations and function names to instruction sequences. This association is what we really wish to create. Note that when we write a program in a high-level language, we only have variables and functions, and the associations are not created. And it is the business of the entire compilation tool chain to construct this association. All right. This association, gradual detailing, is what is called as binding in a formal way. Formally, it is called as binding. You establish a sequence of bindings. That is what a tool chain does. Of course, those bindings are constructed according to certain needs. All right. There is a implicit assumption that there is a definition of the target system. How is it? It's a whatever segmented system, paging is available, and so on and so forth. All of those assumptions go, and accordingly, the tool chain and the association system gets defined. So here is the view. Let us now look at these bindings, how they being created. How are they being created at each level of the tool chain? Actually, let me not call it as a level, let me just call it approximately. So when you define the problem, you say that, okay, given natural number, return its factorial. Then in your mind, you have some bindings. That is, the number num is used to specify input. ANS answer is the label used to collect result. All right. That is what you imagine. So there are some basic bindings, associations that will occur. Albeit at this point, they are not going to be memory locations, but you want these objects to eventually be bound. Only thing that is occurring is now you are clear about which objects you need to be bound. You need to be bound eventually. There are also some factorial unbound objects. Factorial operations are unknown. You only know that you want to compute factorial, but how is not something that you know. Okay. But then you write and use an editor and write a source code. You see that part in front of you on your screen. And when you write the source code, now apart from answer, num, etc., there are a few more objects that now get created. For example, main and factorial. These are explicit bindings, names that get created, and you say that, yes, these are names that I want to create final bindings to. Final bindings. Okay. There are also extra other objects that are still unbound. So argc is unbound, rv is unbound, and so is num. All right. Notice that num is the name of the formal parameter to the factorial function. Okay. Now, when you use the C compiler to translate it to C code, further bindings get established. That is, these names, what are there in the C code, now get detailed out. Everything now looks in terms of operations and register names, which are very, very concrete. Okay. Again, there are some points which are not bound. So the label factorial is not bound. You actually need to pass it through an assembler so that the memory address of factorial gets actually created. All right. But that is going to occur in the next phase. But wait, what is it that we are learning here? We are seeing that as we proceed in the tool chain, we are identifying more objects that we need to create and bind, and that detailing is proceeding one after the other. Every level the detail is added, extra bindings are created. We try to understand what is not bound. In the next tool, we try to create that bindings, and so on and so forth. That is all that is occurring over here. All right. I hope you can see that when we start defining the problem, there are very few objects that get bound. And as we proceed through the tool chain, the detailing starts occurring. The gradual detailing comes down. Gradually, all the bindings that will be required for the final operation on the hardware will be created. Let me look at that a little graphically. All right. On the vertical axis, we have the set of unbound objects. Okay. Which, of course, is infinite when before the process is conceived. All right. That is why no objects are bound. So the number of unbound objects is infinite. But the moment we have defined a certain process, for example, factorial, few entities get bound when programmers try to capture the processes in the program specifications. All right. So programmers realize that we need num, ANS, etc. that we really need to worry about. Still more larger number of objects get bound when the source code is designed and developed, usually by teams of programmers, small or large. After source file, when object files are created, this process increases the number of bindings, the specification, the details, which bindings and their actual associations, they get defined. Okay. Again, some number of objects still remain unbound. But as you see the arrow, the way the graph is going, it is showing you that the number of unbound object reduces at each point, at each stage. Okay. Executables, they remove the binding ambiguity between two object files. So if one object file contains an unbound object, then it has to be resolved by looking at a bound object in another object file. So across object files, whatever are the unbound objects, that must be resolved by linking. That is how executables get created. During processes, there are many bindings get created. Many bindings get created by the loader. For example, the command line arguments. This is the point at which argc, argv get bound. All right. And finally, when it is actually interpreted, that is executed by the CPU. The CPU is a machine language interpreter, right? That is why execution is the same thing as interpretation. So just prior to interpretation, it's possible that there are still some unbound objects. Okay, but that's a technique that is created. So creating bindings even after the processes start is through a technique called as dynamic linking. What is the real idea? The idea is that functions like printf are going to be used by so many processes that it's probably worth having one copy in the memory, and every time a process wants to use it, it is directed to this copy. Okay, this is called as dynamic linking. In other words, the printf name is bound to the actual code after the processes starts running. Okay, that is why I'm saying that it's the linking is occurring after the processes start. This is at times also called as late binding, but we'll worry about that later. But this idea that you can still perform bindings at a later point is can be used in other ways. For example, just-in-time techniques. Okay, well, I have a little things to few statements to say about just-in-time techniques because uh, heap memory garbage collection using or heap memory management using garbage collection and just-in-time techniques are going to follow in this school. But the point I'm making here is this, that the key requirement that we have for final interpretation is this: no object shall be unbound at the instant of final execution, final interpretation by the hardware, at the instant. All right. So think of it like this, that your binary is now a bunch of opcodes. Some of the opcodes represent a jump to the actual printf routine. This jump must exist. This jump must be created before the CPU reaches that particular instruction. So before the instant of instruction, the call to printf gets actually executed, any time before that, this binding must be created. Okay. That is why you can create bindings even after the processes start. That is why you can have dynamic linking. That is why you can have just-in-time compilation. All right. What is just-in-time compilation? Well, we have seen that the underlying machine need not be concrete hardware. It can be a virtual machine. Okay. The binary that is used for virtual machines is called as a bytecode. The idea of using virtual machines is that they are portable across different hardware. This means that the same bytecode should in principle be used on any kind of a hardware system as long as there is a virtual machine running on that hardware. So your program binaries are supposed to be bytecodes. You just take the bytecode from one machine to the other. As long as the other machine has the corresponding virtual machine, this bytecode will run. That is the idea. The only performance problem over here is this, that the other machine may not necessarily give rise to the best performance for this particular bytecode. So what do? We introduce a compiler called as a just-in-time compiler, which will translate the bytecode to the native machine code. And while translating, it will do all the necessary things that it can. In particular, the optimizations. By the way, a compiler can optimize because it can see the entire program, whole program from start to end. That is why it can calculate out that one particular part of the program is useless. The interpreter cannot do that. The interpreter has to take one instruction at a time, or one instruction or one object for interpretation at a time, do it and then go to the next. So it never really has a full view. So the reason why compilers can do a better job is because they can see the whole program. So a just-in-time system will allow the entire bytecode to be viewed, optimized according to what is required by the target system, and then run on the target system. As long as the overall time is saved. Okay, so the time required to execute pure bytecode versus the time required to first compile and then run the native code, if that second time is less, then you have done the job. The just-in-time compiler works. But note that the just-in-time compiler is just really, improving the bindings that are required by the native hardware system. This is the insight that I would like to leave you with. Okay. Garbage collection and just-in-time compilation is something that will be, these ideas will be used later in the school. Okay, so that is why I just mentioned them. All right, here is the summary of that entire picture that we have seen in an animated form, something that I'm creating in some of the things that I'm writing up. But just one single, all of the information condensed in one picture. All right, with that, I'm coming to the end of my second session about runtime systems, where we have looked at some aspects. But before we do that, let's have a set of exercises for you. Here are some, again, discover, explore, study questions. These are a little bit more challenging than before, but it's interesting to, I hope they're interesting to you. So examine the assembly version of a C program and find out the details of construction and destruction of an activation record for a function call. Okay, so we can write a C program, create a C function, and make a function call, and then compile it in assembly version. Fine. And study the assembly version and see how the function call is being implemented by the assembly version. Next question. Can a process discover its own memory layout? And another associated question. Can a process find its own memory layout? So they are slightly different questions. Discover means finding it yourself, and discover means trying to get that information yourself, and finding means you can possibly ask somebody else. All right. And the third question, can you write a C program such that a given callee prints out its own activation record? So think of a factorial program. Can the factorial function print out its own activation? Think about it. You can try experiments with C or yes, maybe it is no, I don't know. So quickly, of programming. We also see how programming gradually introduced, that is, we did that various models of thinking that would each to change. OSS and some software help to complete this process of establishing. Hello, can you hear me?
Hello.
Yes,
Yeah.
sir. Yeah.
Yes,
Oh,
sir.
okay. Because I just got some message which was slightly confusing, but okay. So anyway, I'm towards the end of my story. And runtime environments is all about setting up the bindings that cannot be done statically by the language processors.
But Abhijat, your slides have got unshared.
My slides have got unshared. Okay.
Yes, the perfect.
All is well?
Yes.
Okay. So anyway, I just mentioned this part. So the path from program to a process can be viewed as setting up the bindings gradually. And runtime environments is about that part of the bindings that cannot be done statically by the language processor. Statically meaning by the compilers, the compilation system, the entire compilation system, compilers, assemblers, linkers, and so on and so forth. Okay. On the whole, this is session 1 and 2 together. This is what really it amounts to. And perhaps the summary of this, what are runtime environments? Basically the bridge between the static and dynamic. Here are some references for you, links. Thank you so much for your attention.